In this lecture, we have 4 parts. The first part is ionization of water. We will see how water can react with one another and form different ions, hydronium and hydroxide ions. And from that, we can calculate the concentration of hydronium in order to tell the pH. That's going to be covered in section 2, the pH scale. In the third section, we would look at different reactions between acids and bases. And finally, we will end our discussion of this chapter talking about buffers. So recall from the previous section, we talked about what is the definition of an acid and what is the definition of a base. Right? An acid is something that can donate its proton, whereas a base is something that can accept a proton. So it turns out water in a pure solution can act both as an acid as a base. So let's take a look at that, how that works. But before I forget though, let's mention this word, amphoteric. Right? So this term means that a molecule can both act as an acid and as a base. If it can do both jobs, we call that amphoteric. And we'll see how that is for water. So let's take a reaction between water and water. So we have water here, H2O, and we're going to react that with another water molecule. Okay? Somehow, let's say this water molecule, it's going to go ahead and donate its proton to this water molecule. So this water molecule becomes this species, right? It becomes a hydroxide. Remember that? Polyatomic. Remember that this hydrogen gave its protons away, that's why it has one less proton. And also a proton is something positive, so you lost something that's positive, then you become a negative. That's why it's OH minus. Whereas this guy, he went ahead and took and accepted a proton from here, right? So if this was the original molecule, it accepted this proton, let's say, then now it has an extra proton. Because it has an extra proton, it is positively charged. Remember we call this the hydronium ion? Hydronium ion. Okay? So this, if you can really map it out, becomes that. Right? So this water molecule is a conjugate pair with this hydroxide, and this water molecule is a conjugate pair for this hydronium ion. So let's denote that again. We call this then the acid. In this reaction, this is acid, and this is the base. Because this guy donated a proton, and this one accepted that proton. Okay. So if this was the acid, then this one must have been what? The hydroxide would be the conjugate base. And therefore, this one is, if this is the base, and then its conjugate is the conjugate acid. Now, if this were to occur, then we would, all of our water would be a bunch of acids and bases, right? If pure water does this all the time. It turns out it doesn't do this all the time. Well, it does do this all the time, but it is competing with the reverse reaction. Okay, what is the reverse reaction? If going backwards, if we go backwards, this hydroxide takes a proton from here. If it takes a proton from there, what would this become? It would become water again, correct? If this hydronium ion loses a proton, what would it become? It becomes water again. So that's the reverse reaction. And it turns out the forward reaction is very, very small. It cannot compete. So we can draw it as a small arrow. But still, even though it cannot compete, it still does happen to some extent. Okay, so how much does that happen? How much does water self-ionize? And this was something the scientists was able to measure. So it turns out in pure water, the concentration of hydronium, the concentration of this species here, and the concentration of this species here is equal to one another. At 25 degrees, it turns out the concentration of hydronium is equal to 1.0 times 10 to the negative 7th molar. And the concentration of hydroxide is equal to 1.0 times 10 to the 7th molar. Is that a big number? Times 10 to negative 7? That's a very, very small number, correct? What is that? That's point 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Right? That's 6 zeros, moles in 1 liter. That's what molarity means, right? So that's a very, very small amount. Remember? That's why we say that this does happen, the self-ionization. The water reacts to become those ions, but it turns out it's not that much. It's very small. It's 0.00000. How many zeros is that? 6 zeros? 1 molar per liter. Okay? So it turns out that we can get a constant number from these values. Every time you multiply the concentration of hydroxide versus the concentration of hydronium, you will always get the same number. It's a constant, so we give this a special name. The equilibrium constant of water, Kw. So Kw is equal to, by definition, the concentration of hydronium times the concentration of hydroxide. Now, if you plug that in, what is Kw? 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7. Kw turns out doesn't have units, so the moles we just ignore for now. Punch that in your calculator and you should get 1.0 times 10 to the negative 14. The Kw water at 25 degrees, remember we said this must be at 25 degrees. It turns out at different degrees it is a different constant. But at 25 degrees it is equal to 1.0 times 10 to the negative 14. So that's why I have this graphic here to show us what is the concentration of pure water, the concentration of hydroxide, the concentration of hydronium and hydroxide are equal to each other. If you draw that in a graph of hydronium and hydroxide, and on the y-axis is concentration, 10 to the negative 14 here, 10 to the negative 7, 10 to the 0 there. So notice here that they are equal in height. They are equal when you have pure water. Since the concentration of this quantity and this quantity is, when they multiply to each other, is equal to the same number, it turns out it has a seesaw effect. If this number increases, to keep the product constant, this number will decrease. Oppositely, if hydroxide concentration increase, what would happen to the hydronium concentration? It will decrease. It's a seesaw effect since they always have to multiply to become the same number. If one increases, the other decreases. If one decreases, the other increases. Let's do some calculations to find the different concentrations. You can go in any direction, but let's go ahead and try this one. Using Kw, we can calculate hydroxide concentration. So when a certain amount of acetic acid is added to water, okay, so you have acetic acid, it increased the concentration of hydronium ions to 2.0 times 10 to the negative 3 molar. Okay, so before, if you have just pure water, you have 1.0 times 10 to the negative 7 molar of hydronium ion. But since you're adding acid in there, the concentration has increased, right, from negative 7 to negative 3. That's an increase. So the question is, calculate the hydroxide concentration if this is at 25 degrees Celsius. And again, in this class, we will always use 25 degrees Celsius, but I stated there just to be clear. Because if I say it's at 25 degrees Celsius, then we know what Kw is. Alright, so this is the chemical formula. Just for some background, you don't need it really. Let's do a prediction first. Do you think it's going to be more or less than times 10 to the negative 7? Right? If hydronium concentration, which is acid, is added into here and it increased to 10 to the negative 3, then your answer should be smaller than 10 to the negative 7, right? Because that's the baseline value, 10 to the negative 7. Since we increase the concentration of acid, hydronium, we're going to then decrease the concentration of base, seesaw effect. Let's calculate that to make sure. So I tell myself, what is my equation? Kw is equal to hydronium concentration times hydroxide
concentration. And remember, this was equal to 1.0 times 10 to negative 14. We already know this value, we don't know this value. So we should rearrange this to isolate hydroxide only. Hydroxide then is basically 1.0 times 10 to negative 14 divided by hydronium concentration. Plugging that in, hydronium concentration, as stated here, is 2.0 times 10 to negative 3. Try that on your calculator to make sure that you do get the correct answer. And the correct answer I got for hydroxide concentration is 5.0 times 10 to negative 12. And since it's a concentration, just remember that it is molar. Alright. Now if you are having some difficulties with that in your calculator, you might want to use parentheses on your calculator when you do this calculation. So for example, on your calculator, I would type in 1.0 times 10 to negative 14, all that in the parentheses, and then divided by a parentheses 2.0 times 10 to negative 3, close a parentheses. If you do that, you should get the correct answer. So what happened? Did we get the right answer? Remember from our prediction that we should have a decrease in hydroxide concentration. Is this a decrease from 10 to negative 7? It is, right? So at least we're going in the right direction. Let's do another problem using kW. In this one, I am asked to calculate the hydronium concentration if hydroxide concentration is given. So when a certain amount of liquid ammonia is added to water, it increases the concentration of hydroxide ions to 4.10 to negative 4. Again, at pure water, both hydronium and hydroxide is 10 to negative 7. I'm saying that it's going to increase your hydroxide concentration upon adding this base to become 4.0 times 10 to negative 4. So hydroxide has increased. What do you think hydronium level is going to do? It's going to have to decrease. So our answer should be a decrease. Alright, so let's do this calculation here. Again, I want to say start with Kw is equal to hydronium concentration times hydroxide concentration, which is always equal to 1.0 times 10 to the negative 14. This time we have hydroxide concentration, so hydronium concentration is what needs to be isolated, which means you have to divide both sides by hydroxide concentration. Divided by hydroxide concentration, which is this value right here. Right, so that's 1.0 times 10 to the negative 14 divided by 4.0 times 10 to the negative 4. Do that on our calculator and you should get 2.5 times 10 to the negative 11 molar. Again, checking with logic here. We said that it's going to decrease in concentration because hydroxide concentration increased, so hydronium concentration should decrease. Is this a decrease from 10 to negative 7? Yes, this number is smaller than 10 to negative 7, so at least we're going in the right direction. So let's illustrate that here one more time. In the beginning, we have them at neutral solution, they're equal to each other. So in the first case, we saw that when we added acetic acid into our solution, hydronium concentration increased, therefore decreasing the concentration of hydroxide. In our second example, when we added ammonia into our solution, it released and increased more hydroxides, and therefore to balance this out, our hydronium concentration will decrease. This again is what we call the seesaw effect. They must increase or decrease accordingly to have that balance at the end. Alright, now let's do a checkpoint. Right. Use the ion product of water to calculate the hydroxide concentration of an aqueous solution with hydronium concentration of 6.0 times 10 to the negative 4. Okay, so you ask yourself, when you see a problem like this, what do I know? I am given hydronium concentration. I am asked to find hydroxide concentration. What is not given to me, we would know, is the Kw, right? The ion constant of water. So the equation we always should conjure up is Kw is equal to hydronium concentration times hydroxide concentration. We know this and we know this. So we rearrange this to give us the hydroxide concentration. This is 1.0 times 10 to the negative 14 divided by 6.1 times 10 to the negative 4. We do that and we get 1.6 times 10 to the negative 11 molar, which is answer C. Alright, so that was the ionization of water and Kw, the constant of that. So the take-home message is that two things. First, if you're given the concentration of one species, you can calculate the other by using Kw. The second message is the relative concentrations of hydronium and hydroxide. In pure water, they're equal to each other. But as soon as you add some acid in there, the hydronium concentration will increase. And to make the Kw become a real constant, it must stay constant, then hydroxide concentration will decrease. On the opposite case, if you have pure water again, if you add base to this solution, then hydroxide concentration will increase. To keep Kw constant, then hydronium, to counterbalance that, must then decrease. So have more practice with that.